This is further statistics 1 from 2020. All right, let's just go into it. So Poisson distribution, a rate of 2 every 5 minutes. Now, the first thing is about a 1 hour period. So let's scale this up. So 5 times 12 is 1 hour, 60 minutes. So that times 12 is 24. So let's do a Poisson distribution with lambda 24. And what's the probability of exactly 26? Just use a calculator for Poisson. PD is going to be for exactly equals to, we get this. And then at least 21, so that's 21 or more. That's, of course, equal to 1 minus less than or equal to 20. And you can do a Poisson CD in your calculator to get this probability there, and then you get the answer there. A rival supermarket opened up, and it says that over a randomly selected 40-minute period, the customers is found to be 10. Do a significance test. So, of course, H naught is going to be, okay, so 5 times, what is that? 5 times 8 is 40. So 2 times 8 is 16. So we'll say null hypothesis is lambda is 16. H1 is lambda is less than 16 because we're going to just have a look for evidence of a decrease. So we're going to do X towards Poisson with 16. And let's find the probability of there being less than or equal to 10 people in that time. Now, of course, we can just do Poisson CD for this. We'll get this probability here. And that's greater than 0.05. So it's not in the critical region. And therefore, we will just keep H. We won't reject H naught. We'll just keep it. So I think that's done. A further selected 20-minute period is observed. So 20-minute period means scaling this up by 4. So there'll be Poisson 8, I think. Given the true rate is now this, so it will actually change, and this is the true rate. Type 2 error. Now, a type 2 error occurs when you accept H naught, even if it's wrong, when it just happened to be wrong. So what we'll do is we'll say, well, H naught is essentially that this is distributing in the same way as it was. So 20-minute period, times that by 4, times that by 4, with 8 here. Get out the Poisson tables and look for where the critical region is. So for a 5% test, which we'll just say here, for a 5% test, the critical region will be this one here, because that's less than 0.05. So critical region is X is less than or equal to 3. And so we'll accept anything bigger than 4 or more. Okay, so what's the chance of us accepting or getting 4 or more? What's the chance of us getting 4 or more? Because if we get more than 4, we'll accept H naught. What's the chance of getting that, given that the distribution is actually following this here, whereby in a 20-minute window, you're actually only going to get 4 customers. So accepting H naught means being out of the critical region, which is this, given that it's wrong and we're actually following this thing here. So all we have to do is work out the probability of this with this distribution, which is, of course, 1 minus P of X less than or equal to 3, because, of course, we can just swap that around, and then just find that in a calculator, Poisson CD or whatever. You get this, which is this, and we'll have our answer. Question number 2. So this is a binomial. Is this Poisson a good approximation? You need n to be large and you need p to be very small, and neither of those two things are really particularly true here. So I'm going to go with no. This is probably not a good idea for this one here. Say the assumption for this to be distributed as this. It's always a good shout to whack out the word independent. They've got to be independent. Just if you're unsure, just write the word independent and you'll be good. Find this here. So what's variance of W? So the variance of a binomial is NP times 1 minus P. Of course, n is 10, p is 0.4, so we just shove those numbers in, we get this. And so we're looking for the probability of x plus y to be less than 2.4. But x plus y is just following a distribution of Poisson with lambda 7. So imagine this is just a letter x, and sorry, a letter z maybe, and this is a letter z. What's the probability of being less than 2.4 if you're following a Poisson of 7? Well, Poisson needs whole numbers, right? So this is less than or equal to 2 is the same as. And then we can just use a calculator, Poisson CD, use x as 2, use lambda as 7. And we'll get this here. Question 3, so they put 4 reds and 1 blue in a bag. And basically, whoever picks the blue first, they take it in turns and they always put it back at the end. If you pick a blue, you win and the game ends. So find the probability Suzanne selects a blue counter on her 4th selection. Well, for that to happen, she can't have got a blue on her first, and nor can the other guy, John. And then they must have both missed on their second and both missed on their third. Her 4th selection is actually the 7th go at this, right? They each have 3 goes first, so that's going to be 2 times 3 is 6, and the 7th go is apparently the one that picks out the blue. So this is a geometric thing because we're just picking out, it's the first time we get it, we finish, and we want x to be 7, right? So to get this far, we want x to be 7. We want there to be 7 goes because they both have 3 each, and then on the 7th she wins. So we just put 7s here. P is, of course, 1/5, 1 over 4. Sorry, 1 plus 4 is 5, so 1 over 5. And then we just type that in, we get this. Probability that the counter is selected on or after John's 3rd selection. So John's 3rd selection, so it goes Suzanne, John, Suzanne, John, Suzanne. That's 5 goes, and then John's 3rd selection will be the 6th go. So we want the probability of x is greater than or equal to 6. which is, of course, 1 minus the probability of x less than root 5, which you could do, or you could just say, okay, well, for this game to last longer than six or longer goes, you just need to dodge five. You just need to get 5 reds in a row. Like the probability of getting a red is 4/5. If you just get 5 reds in a row, it doesn't matter what happens after that. 5 reds in a row means the first 5 goes don't work, and then it would just be the 6. So we could just use that formula if we want to. There are other ways of doing that, of course. Find the mean and standard deviation. Thankfully, those are right here. The standard deviation is the square root of the variance, so we just pop in 1 over p for the mean, which is very easy. And then the variance, we just square root this, and we put p in, and we get some answer as well of this. Find the probability that Suzanne wins the game. Okay, she could win the game on the first go. She's got a 5th chance of that. If she doesn't do that, though, so 4/5 of the time, when she doesn't get it on the first try, she can hope that John also doesn't get it, which happens with chance 4/5, and then she'll get it on her second try. So she could get it on her first try, or if she doesn't, which is the remaining 4/5 of the time, John has to miss with 4/5, and then she gets it with 1/5 chance. Or, of course, she misses again, and you end up with this. So she misses the first go, John misses, she misses, then John misses, then she hits. That's essentially what this is. And I don't want to write out another one. What essentially happens is you just throw in an extra 2 4/5 to represent her missing, then John missing, before she can have another go. So yeah, we just throw in an extra 4/5, and this is going to be an infinite sum because technically this could take forever. And the ratio is, well, the first time is 1/5. The ratio is just 2 lots of 4/5, which is 4/5 squared. And an infinite sum based on our A-level maths is just going to be this. So it's going to be a over 1 minus r. This is less than 1, which is good. So it's going to be 1/5 over 1 minus this. And we can just sum that for 5/9. It makes sense that she has a slightly higher chance of winning since she gets the first go. Okay, next one then. So find variance of x. So we can use this formula here, e of x squared minus e of x all squared. So e of x is, of course, just this times this, plus this times this, plus this times this, plus this times this. So I'll just type that in, and I'll get this. And then, sure. And then e of x squared is this squared times this, plus this squared times this, plus this squared times this, and so on. We get this. Of course, when they square, that's kind of interesting. It becomes positives, which is why this number is much bigger. And then we just do this, take away this thing squared, and we get, I think, 9. Good. The discrete random variable is defined to be this. When x is negative, y is this. So let's make a table, and I'll replace the x's with y's here. When x is negative, y becomes x squared. So this becomes a 25. This becomes a 4. When x is positive, y becomes 3x minus 2. So 3 times this is 9, minus 2 is 7. And then this is 12, minus 2 is 10. What's the probability that y is less than 9? Well, it's just this plus this, right? I don't know whether I just never animated that in. Oh, no, it comes in there. Okay, this plus this, and it equals that there. Find e of xy. Now, e of x squared was just when you did this times itself, then times the probability. It's just x times x, right? So when you have xy, that's just x times y. So it's just this times the probability, plus this times the probability, plus and so on. And we end up with this eventually. I just type it into the calculator, obviously, and move on. Question number 5 then is it's the chi-squared question. So we've got this. He selects 40 samples of 6 pins each, and we get these results. So in 19 of the samples, none of them were wrong. In 11 samples, you got 1 out of the 6 is wrong, and so on. So let's find the total here. So 0 times 19 plus 1 times 11 plus so on, we get 36. Now, how many totally did he test? Well, not 40, but 40 times 6 is how many pins he actually tested here. So we just do 36 divided by that, and we get this number here. The engineer suggests that the number of defective pins in the sample can be modeled using a binomial distribution. Using the information from the sample above, so from here, to test at 10% significance whether data is consistent with this. Now, this is a bit weird. It's given you the test statistic, but you still have to do basically all of the work because, and I'll explain why. So you do the expected one here. So this is a binomial with 6, and then the probability is 0.15. And now what we need to do is we need to work out, okay, what's the probability of x being 0? Just use a calculator here. We get this number here, which goes, or you times it by 40 first, of course, because there are 40 samples, and that gives you this number here, which goes there. And then you do the same thing. So p of x equals 1, times it by 40, you get this number, and so on, and so on, and so on, and so on. And the reason you have to do all this is because even if they've told you the value of the test statistic, you need to know how many columns are going to be collapsed here so that you can do the degrees of freedom bit. So you need numbers to be over 5. Now, if you collapse all of this together, you still don't get anywhere near 5. So you have to collapse it in with this one as well. And our new table looks a bit like this, where everything's collapses inwards like this here. And we only have 1, 2, 3 columns, which means our degrees of freedom are 3 columns minus 2. Now, it's minus 2 because these have to add up to be 40. So that's one restriction. The other restriction is that we just calculated these expected ones. And there's a note in the textbook here. If the parameter has been calculated, then it's a restriction. And we just calculated those using this. If it's just guessed using an estimate, then that's not a restriction, but these were calculated. So we take away 2 here, and we get 1 degree of freedom, which means in our chi-squared table, we're doing v as 1 here, and we're doing 10% significance, so we're looking for this number here. And their chi-squared is less than that, so it's not in the critical region, and we'll say this is consistent with the model. So we basically did all of the work except doing the OI squared over E minus N bit. We basically had to do everything else. Anyway, the engineer then discovers that the counting was incorrect, and actually this is the distribution. So notice how they made a mistake here. It's actually 6 and 3, and then they also made a mistake here. Does that affect any of the things that you've just done? Well, you can go from the top, maybe work out the total number of pins that are wrong, and it actually still turns out to be 36 if you do that. And then, of course, work out the total. Well, of course, that means the probability is the same because you got the same number in total. So, okay, so the binomial distribution bit was fine. The probability is still fine, so that was okay. Now, what about the rest of it then? What about the rest of the things we did? Well, you're still going to have to collapse these columns in. Like when we do um, our expected things here, all of these columns would still collapse into the second one, right? Because this number is a bit more, but because these numbers don't affect the expected values, do they? Because the binomial distribution hasn't changed. So all these would still collapse in here. And this essentially then gets all of these, and this would be a 10. And this also just gets all of these, and this would also be a 10, and the expected value wouldn't change. And this is for when we work out the x squared bit, and we do OI squared over E minus N, none of that is any different. The expected answer is different because the binomial is the same, and none of this is different because it would still be 1911, and then this would be a 10 because it takes all of these like this did, and nothing has changed. So no, nothing would change about this at all. And the degrees of freedom would still be the same because you still have 3 columns and still have 2 restrictions. So yeah, everything would be exactly the same. The probability generating function question then, so write down the value of p of x equals 3. So when you have a p of x equals 3 for one of these questions, that's just the coefficient of t to the power 3. And of course, the coefficient of t to the power 3 here, when you expand that out if you want to, is just 0. So that's 0. P of x is 4. That means the coefficient of t to the 4 is this. But the coefficient of t to the 4 is b squared over 64, having expanded that out. And we get b is plus or minus 5, except the positive constant, so b is 5. And then find the probability that x is 2. Now, I can actually find a, because I can use this, which you always have to use during the paper. So remember this result. Gx of 1 is 1. So put that into here. And we get this, b is 5 and t is 1. So this becomes this, times by 64 square root. You get this. A could be, I guess, minus 13, but it's definitely not. It's going to be 3 because of this. And so we have both of our things. So this is our function here, subbing it into there. And p of x is 2. That's just the coefficient of t squared, which is 30 over 64. And e of x, now there's a couple of ways of doing this. You could just work out. So the initial way I did it was I said, okay, well, you could get a 0. And a 0 has probability 9 over 64 because it's because the probability that x is 0 is the coefficient of t to the 0, which is just the constant. So we've got that plus 1. This is if x is 1. But the probability of x being 1 is 0 because there's no coefficient of t to the 1. And then 2 times the coefficient, the probability of getting an x is 2, which is the coefficient of t squared, which is 30 over 64, plus the next one, which is 0, plus 25 over 64 times 4. And you could work that out and you get this. Alternatively, you could remember this result, which is in the textbook, but not in the formula book anywhere, which is that e of x is equal to g of x dashed evaluated at 1. So you just differentiate this result here. And I hope you can see when you put in 1 to that, you're going to get the same number that I did here. Random variable this is another super useful result to just know it's not in the formula book. But when you do a thing like this, you have this result here where that 2 goes there and that 3 goes there. So all we have to do is it's probably easiest to take the original function and just put the input as t cubed, which makes that a t to the 6, everything else the same, and times the whole thing by t squared at the end. Of course, a and b are 3 and 5, and we end up with this here. So yeah, another super useful result to know there. And the very last question then, we've got a dice labeled this. We're assuming it's fair, I guess, for the starter list. I suppose 45 times mean score as is calculated. Assuming the die is fair, yeah, there is, and using a suitable approximation finds this. So firstly, we can work out E of x, and E of x on a fair dice is 3.5, just because it's right in the middle of those, and it's a fair dice. So you can do some calculations if you want, but I'm just going to say it's that. E of x squared, maybe you actually have to do some calculations for. It's 1/6 times this squared, plus 1/6 times that squared, plus 1/6, and so on. I just factorized out the 1/6 and then just added the squares together up to 6, and I got this. And so therefore the variance of x is this minus this squared, which is equal to that. And now I can approximate this sample here by using a normal distribution with mean that we worked out, 3.5, and variance is going to be this variance over n, the number in the sample. So this is the variance of the original thing divided by n. This is the formula that you kind of end up using. Of course, this simplifies out to be that. And now we're just looking for the probability of this S bar to be less than some number such that it's 0.05. Now, what I've done here is this is actually going back to just regular A-level stats. You do x minus mu over sigma equals, and now this is the value for area 0.05 on the standardized normal graph, just the one with mu 0, sigma 1. So that's the value that we get there for 0.05. And again, this is just the x minus mu over sigma thing. Sigma, remember, is root of this, because this would usually be written as sigma squared. So sigma is root of that. You rearrange this, you get k as that. And explain the relevance of this. Well, the central limit theorem essentially says that the sample mean is normally distributed, and that gets better as n gets larger, and n is already fairly large. So you just have to say something like that. Alicia considers the following hypothesis: H0 is fair, H1 is not fair. If that and that, it's going to be rejected. But now the power of a test, now we've got the true distribution now, so the dice actually turns out is not fair. But anyway, the power of the test is being in the critical region when H0 is false. So it's essentially, I mean, that's what you want, right? You want to be in the critical region when H0 is false, because if you're in the critical region, you'll reject H0. So what's the probability of being in the critical region when H0 is false? Now, the probability of being in this critical region here, so I've got this here. This is the actual distribution, because of course if H0 is false, I need to use the actual distribution here, and that's mean for variance 3 over 45 still. Still needs to divide by n, just like before. And now the probability of S being less than 3.1, because that's when she'll reject it. You can type that into calculator as a very, very small number. The probability of being greater than 3.9 is, of course, 1 less than the probability of being less than 3.9. Type that into calculator using this. Remember to use the root of this when you're doing sigma, and you get this, which is this. Add those two results together, and you get this. So we've added the two critical regions together, which gives us the total probability of being in the critical region, and we've done it when H0 is false, when we're actually using the true thing here, and we've got this. So this is the power of the test. Describe what would happen to the power if Alicia were to increase the number of rolls of the die. This is a very standard result. The power gets better the more you do it. And the reason for that is if you increase the number of rolls, the variance will go down. Yes, to decrease in variance as n goes up, as the number of times you do it goes up. So decrease the variance. Decreasing the variance will essentially increase this probability, because this is already below the mean. So if we decrease the variance, we'll get a larger and larger amount being above 3.9. And so the power would end up increasing because this would increase, and then we add it to something else and we increase. So yeah, I think that's the whole paper done. Thanks for watching, and I'll see you next time.